Alright, so I'll be reviewing the structure and model of atoms. This is a very basic topic, and it's one of the first few you'd go through in general chem. So to get started, let's firstly talk about the composition of atom and like a little more of what it is. Let's write the atom because it's singular. Okay, so when we say this, we can say that the basic structural unit of an element is an atom. And so as a result of this, we can say that atom retains the chemical properties of the element. Since it's part of an element, it's the basic unit of an element, it retains the same chemical properties. So an example of this could be like a copper atom. It will have properties of copper, so it will be shiny, it will be malleable, so on and so forth, even ductile, you could say. All right, so that is the basic composition and what it basically means. The main thing is that it's a basic structural unit of an element, and that it retains the chemical properties of the element which it's part of. And in an element, often there are like billions of atoms. So we can just mention that elements are composed of billions, even more, like there's way too many of them. In addition to this, an atom is usually, now that we've spoken about the definition, let's talk a little more about the composition itself. So let's actually divide this up so that we have better understanding here. So this definition. Let's now move on to the actual composition of what an atom contains, I guess. And so over here we can say that it contains three things. Let's do one: proton, neutron, and electron. So these are known as subatomic particles or subatomic fragments, and their role is to provide a charge to the atom in a way. In standard conditions, it's usually neutral. That is because this is a positive 1, proton gives a positive 1, electron gives a -1, and neutron gives a 0, so these two just cancel each other out. And so as a result, in neutral conditions, it's usually 0, but in the cases of ions, the charge, when an electron is lost or gained, the charge increases or decreases, it becomes positive or negative. And we'll get into that later, but that's the basic concept, and that's what it is composed of. And so as such, we can just say here that this is positively charged, this is neutral, and this is negatively charged. One important thing to know is that the proton number never changes. It's always the electron number that changes when the formation of ions is involved. So that's something to know as well. Let's now move on to the nucleus of an atom. This also comes under the composition. So we'll just mention here nucleus. Now we know that the nucleus is like the central, really dense part of the atom, right? That's a pretty common thing to know. But we can say the nucleus is a small, dense, positively charged region in the center of an atom. So we can also say that the nucleus is composed of protons and neutrons. So we mentioned before that normally the atom as a whole is usually neutral. However, the nucleus is the central core of this atom, and the central core is always positive, and that's because of the presence of only protons and neutrons in the center. So as a result, since the neutrons have no charge at all, and since the protons have a positive charge, there's an overwhelmingly positive charge in the center. And the negative charge comes from the rings that surround the central nucleus, and they have electrons in them in regions, clouded regions. And so they provide the negative charge, which causes the whole overall atom to become negative. But the central core is positive and the outer rings are negative, if we're talking specifically. And let's just mention that actually about the outer rings. Surrounding the nucleus is a diffused region. I just told you it's like a cloud. So it's like a diffused region of negative charge. It's just all over the place. And this is provided by electrons. right. Okay, one more thing to just go over. I'll just go and do this here. So protons and neutrons are typically pretty big in relative terms, in very relative terms, to the electrons. So that's something to know. The protons and neutrons are about the same size, and the electrons are way smaller, like way smaller. So the proton and neutrons are something like 1, and the electrons are like 1/27. It's ridiculous. They're tiny. So that's also something to know, I guess. And yeah, all right. Let's now move on to the next section of this, which is the symbolic representation of elements. Symbolic representation of elements. Now that is pretty fancy jargon for just the way you write elements and their symbols, and this is a pretty fundamental high school level thing that most people know. But let's just go over it really quick. So when we talk about this, we usually have two things that we refer to. So the first one is atomic number, and I'm going to give you an example, and that example is going to be referred to by Z. And then we have something called mass number, which I'm going to refer to as A. And then we have something known as X, and that's just your element. So it's just, we can just say element. All right. Now let's just define what each of these things are. So an atomic number is the number of protons in an element. The mass number is the number of protons plus neutrons. See how we don't consider the electrons at all? It's because they're so tiny, they don't have any effect on the mass. And these two things have to do with the mass. So as a result, we only consider the number of protons, and then in the mass number, we consider protons and neutrons. And X over here is just the symbol of the element. Symbol of element. And when we typically write this, we refer to it by, so let's say this is an element, any element, X, for example. And let's say it's A, as we said, that's the mass number, so that's the proton and the neutrons. And then it's Z over here, which is only the number of protons. So that's how you represent elements based on the number of protons and neutrons. And one more thing to actually note is that, this is actually quite important, maybe asked, protons determine the identity of elements. So an example of this could be, your carbon. Carbon has 12 as its mass number, which is its protons and neutrons, but its proton number, which is its atomic number, is only 6. So that's what tells you that, oh, that's carbon. Similarly with oxygen, it's 8. With nitrogen, it's 7, so on and so forth. That's how you represent elements. Anyways, let's move on now to isotopes. This is also another term, this is all pretty much a recap. It's really straightforward stuff. You've probably heard it a billion times, but it's good to go over again. The devil's usually in the details with this stuff. So when we define this, we say same number. Wait, let's just write that a little better. Elements with the same number of protons, but a different number of neutrons. So what's changing here is the mass number, basically. Let's just actually write atoms out of elements, because it's not actually the element itself. The atoms are what makes it up. So atoms of elements with the same number of protons but a different number of neutrons. Or alternatively, you could say same atomic number but different mass number. And so examples of this are carbon 12 and carbon 13. So what's happening here is that the mass number changes because the number of neutrons in this case is 6, because we know that carbon has 6 protons, so the other 6 are neutrons. But what happens here with this isotope is that there is still 6 protons, that doesn't change. But now that the mass number is 13, that means that there's 1 more neutron. And so as a result, the mass number increases, basically. It can also decrease, it's not really like only an increase. In the cases of, for example, fluorine, it changes. Many other cases as well, there's many examples, so on and so forth. Let's now move on to the use of isotopes in modern medicine, because it's actually really useful in quite a lot of things. And this is actually the medical application, which is what matters more than most of the definitions and stuff. That's to build a base, and it's obviously really important. However, in medicine itself, it's quite important. So let's just write isotopes in medicine. All right, so for this, Usually what we use are what we call radioactive isotopes. Radioactive isotopes. And we use this because it emits particles of energy that can be used to trace the behavior of biochemical systems. Now that may just sound like a whole lot of jargon, but it basically means that the isotopes emit radiation, as it says, radioactive, and this can come in form of rays and things like that. Not necessarily get into the detail for that right now, but as a result of them emitting this, it allows us to trace this in biochemical systems, and that's just a fancy way of saying in our bodies, and also in other things actually, but mainly we're more interested in our bodies. But let's get into a few examples, and hopefully that'll make it a little easier to understand. Firstly, let's talk about carbon-14. So this has so normally carbon is carbon-12, so in that case there's 6 neutrons, but in this case there's 8 as a result because there's 2 more, and it's used in what we call radioactive dating. And this is really important in archaeology. It helps us basically determine how far back a certain fossil or things like that or organisms were. And another thing which is quite useful in is plant photosynthesis determination, plant photosynthesis steps determination. So it's really helpful in those two things. Really crucial thing, especially for radioactive carbon dating. It was like a huge thing for archaeology and even for biology, really. And yeah. After that, we have this other example, which is, I guess, more important to us humans: phosphorus 32 and phosphorus 33. And this is used to research in genetics mainly. So really revolutionary for genetics as a whole. Very important for us, obviously. Another thing which is actually really important and really quite cool is what we call selenium-75, and this one is really important in protein studies. Another example could be strontium-85. Now these are all isotopes. They have different number of neutrons, and this is used in metabolism and also, I guess, in bone formation study. Alright, so those are some examples of the use of isotopes in medicine. Let's now move on to ions. We mentioned this before, and we'll just go over it really quickly. It's also relatively easy, and it's the last section of this lecture. Alright, so what are ions? We define them as electrically charged particles. And there's 2 types of ions that we refer to. One's called an anion, and one's called a cation. Now, one of them is positive and one of them is negative, but that happens as a result of gain or loss of electrons. So an ion is formed due to the gaining of electrons, and so as a result it's negative, more negativity, more negative basically, and as a result it forms negative ions, I guess you could say. And in the case of cations, it's the opposite. It loses electrons, and so as a result it forms positive ions. And I guess one way to remember this is was quite helped me in when I was studying this. So cat ions are positive. So it's like a cat and paw. It really helped me learn it. I hope it helps us with you as well. But I think it's a good way to think about it, really. And you associate something funny like that with it. It'll stick with your memory more, I guess. Yeah. Anyways, so that's one way of remembering it. And if you know that cations are positive, then anions are just the opposite of that. So pretty good way of remembering, in my opinion, if I do say so myself. One last thing that we need to know is the equations that are used for the formation of anions and cations. I was going to do that really quickly. It's really quite straightforward and just something you have to memorize. The positioning is really important, so watch here. We'll take the example of a neutral atom. This is F, it's anything. It's fluorine really, but in this case it's anything. So as you see here, it gained a negative electron, and so what does it form? It forms an anion. And you guessed it, with the other one is the other way. It donates, right? So in this case, the electron's on the other side of the arrow. Over here on the left side, on the other, in the case of cations, on the right side. So you have your electron again, but this time you have an Na plus because this donated an electron and became positive, and so this is a cation formation. Cations are positive. Positive. Anyway, so that's how I review this really basic core level topic. One really way of perfecting this is practicing the like writing of different like ions and their configurations, I guess, like their atomic and mass numbers. Really helps you perfect that. But that's really a high school level thing. It's not really very important in medicine. But ions are just all over the place in medicine, in muscle contraction, and like your co-transport functions, and in literally every function in the body you have your ions. So really important to know, and it builds a good basis on that. And obviously knowing the difference between anions and cations, and knowing isotopes and the uses of isotopes in medicine also really important. And the rest is pretty basic, I guess. But just because it's basic doesn't mean that you can skim over it and not study it properly. So I do recommend you do review this once more. And yeah, that's about it for this. Thank you for watching.